Okay, welcome to FuzzCon Europe, the Web Security Edition. My name is Matthew Smith. I'm a professor at the University of Bonn and the Fraunhofer FKE, and it is my great pleasure to welcome you all to this evening's talks. Well, I say this evening, since it's evening in Germany where we're currently located, but we have over 500 registrations from all over the world and across all time zones. So depending on where you are, good morning, good afternoon, or good evening. It is lovely to have you with us. We're going to be having a couple of talks and a panel discussion this evening, and to take part in the discussion, the best thing would be if you register for our Slack channel. You can do that by going to fuzzcon.eu, and there should be a big button saying Join Slack Community. Since in past events, there's been a little of trouble for everybody to get signed up there. We'll wait a few minutes so you can do that in peace and quiet without having to split your attention. There also sometimes seems to be a problem with people signing up to Slack with their Google Mail accounts. So if you're having trouble, maybe try an alternative email address and see if that works for you. So like I said, we'll give you a few minutes before we actually start with the program so everybody can get set up. If you don't want to use Slack, you are also welcome to use the chat here in Click Meeting. And you can also message me via Twitter if you prefer that. So it'll be organized as follows. We'll be having the presentations, and there'll be a Slack channel for each of the talks. And you can then ask questions there. If you don't want your name to be visible for one of the questions, as I said, feel free to send me a direct message via Slack or Twitter. My Twitter handle is m42smith, and then I'll pose the question on your behalf without divulging your identity. Okay, so everybody get settled in, join the Slack community, and we'll be starting shortly. For the Slack URL, you can go to fuzzcon.eu. You'll get the URL there. Okay, it looks like people are getting into the Slack channel. That's excellent. Okay, if there's anybody who wants to change the UI language of the Click Meeting interface, you can find the language settings in the top right-hand corner of your browser window. There's a little kind of a globe symbol next to the language. So if you want to change that, you can click there and change it. Ah, yes, and if anybody's having trouble with the stream and Click Meeting, there's also a live stream on YouTube. The link was just posted in the Click Meeting chat. Okay, so since we've got a few new people joining us, I welcome you all again. My name is Matthew Smith, and I'll be leading you through today's FuzzCon Web Security Edition. I'd like to thank Code Intelligence for organizing this again. It's great to see so much interest in this area, and I'm particularly happy to have been reinvited back to lead the conference for this topic. So when I started off my career as a PhD student almost 2 decades ago, I actually started in web apps. So not security, just plain web apps. That was the area I was doing my research in. And at the time, I had no interest and no knowledge about security. And because of developers like me, it is excellent that there are people like you and people who fuzz web apps, because it is sorely needed. Because, of course, not all developers think of security, and securing web apps is actually quite a hard thing to do. And to talk about how we can fuzz web apps, we have an excellent selection of speakers. In order of appearance, we have people from the OWASP SAP team. We have people from Microsoft, Code Intelligence, and Google, who will all be talking about their area of expertise. And in the end, we'll have a panel discussion where you can also then pose more questions, which can be then answered by the entire team. Okay. I hope you've all managed to join our Slack community. So that'll be the main area where we organize the discussion. You can find the link to join on the fuzzcon.eu website. Scroll down a little bit. There's a button called Join Slack. And that should take you through the steps. And if you want, you can just then ask questions in the channel for that session. Alternatively, if you don't want to be or don't want to ask a question publicly, just send me a private message through Twitter or Slack, and I'll ask the questions for you. And with that, I think we can go over to our first talk. Simon Bennett is project lead at OWASP SAP and is a distinguished engineer at Stackhawk, a company that uses SAP to help users fix application security bugs before they hit production. He's talked about and demonstrated SAP all over the world, including Java 1, FOSDEM, OWASP AppSec, all editions, so EU, USA, and Asia Pacific. And prior to making the move into security, he was a developer for 25 years and strongly believes that you cannot build secure web applications without knowing how to attack them. And on that last thing, I couldn't agree more. And of course, many people don't know how to attack them, and that's why we have so many problems today. So I'm really looking forward to Simon's talk. And with that, I'll hand over the mic to you, Simon. Great to have you here.
Thank you very much, Matthew. Hopefully you can see me and hear me okay.
Yeah.
Great. I will now share my screen.
Yeah, that looks good.
Great. Okay, so as Matthew said, My name's Simon Bennett, and I've actually got a confession to make. I don't consider myself as a fuzzing expert, unlike the rest of the speakers on this in this conference. So why am I here? Well, I'm the project leader for the OWASP attack proxy. So hopefully I know a little bit about attacking web applications. And that's why I'm going to be talking about why fuzzing web applications is hard. I'm also on the Open Source Security Foundation Security Tools Working Group, and as I mentioned, also work at Stackhawk. So I'm going to start off with what ZAP is, because that's my claim to fame, really, and I guess the only reason I've been invited here. And so ZAP is a tool for finding vulnerabilities in web applications. Like all OWASP tools, it's completely free and open source. And we're saying it is the world's most frequently used web application scanner, or DAS tool. This is a claim we've made many times. No one's challenged it, so it must be true. But I think now is a good time to talk about terminology, because terminology when it comes to security tools is actually a bit tricky. And this is something we're starting to look at as part of the OpenSSF Security Tools Working Group. And it's something I kind of looked up for this talk as well, because there's a difference. I think there's a difference between DAST and fuzzing, and it's not something that I haven't really found good definitions of any of these things. And I must admit, I tend to describe ZAP as a web application scanner rather than DAST tool. But I think there's a lot of terminology out there, and a lot of them are kind of marketing led. So let's first of all start at what is the difference between fuzzing, or differences and similarities fuzzing and DAST. And this is going to be really high level, so apologies to the people on this call, and particularly people on the giving talks about this stuff who know a lot more about this than I'm covering here, or that I do. So I think that the big similarity is they both attack running systems. So it's it's not the same static source code analysis where we're looking at the source code. We actually have to have something running, something we can really attack. But fuzzing is really, we do a lot of attacks as part of fuzzing. I've said random. I mean, there's people who know about the stuff will know there's a lot more to it than that, and it's not really random. There's mutations, all sorts of fun things. But at a high level, fuzzing really is about, at a very simplistic point of view, is sending lots of attacks. Whereas in DAST and web scanning, we actually don't try and do that. We try and do very highly targeted attacks. So we don't try and throw loads of things at an application, which kind of surprises some people. So why do we do that? Why do we not try and do as many attacks as we possibly can? And that brings us on to the first of the problems that we have. And I should mention that in ZAP, we do support fuzzing, but we treat it as a manual process. So it's something's it's automated. You can automate it with ZAP, but you have to control it manually. And this doesn't really fit in with the kind of the traditional view of fuzzing, which is completely automated. But there are problems with fuzzing web applications, which is the subject of this talk. So, and the first of these problems, the really big one, which is why DAST tools don't make loads and loads of requests, is time. Time is the enemy of DAST tools. So in ZAP, we do passive scanning, and passive scanning is where you kind of look at the requests and responses and just see potential problems based on those. And then we have active scanning, and this is where we're doing the attacking, the kind of equivalent to fuzzing. But we have different rules, and we have different rules for different types of attacks. So we'll have rules for cross-site scripting, SQL injection, all these things. But with ZAP, you can have different strengths for every single rule, every single active rule, that is. And the strengths really come down to the number of attacks we make per parameter per page. So we have a low strength, which is roughly usually around 6 requests per parameter per page. Medium strength, which is around 12. High strength, which is around 24. And then we do have an insane level, which can be hundreds of attacks. And we don't recommend this for automated scanning. Now, these numbers are actually going to seem really low to anyone who's been involved in fuzzing. It's a tiny number of requests. And what we're trying to do is we're trying to get the most bang for buck. We're trying to find as much as we can, but with as few requests as possible. Why do we do that? Well, let's have a look at an example site, an example application we might want to attack. In this case, we've got 100 pages. We've got an average of 5 parameters per page. So that means we have 500 individual targets that we need to attack. And DAST tools like Zap, we attack at 1 parameter at a time. So we have about 20 core or release quality active scan rules, and medium strength is the default. So we're talking around 12 requests per scan rule. So we're looking at, we've got 500 targets, 20 rules, 12 requests for each one. So 120,000 requests to attack this application. This means we're talking about 20 minutes if your application is responding at something like 100 requests a second. And if you can get only 10 requests a second out of your application, then it's 3.3 hours. Now, these kind of responses, requests per second, might look very low to some of you. Surely modern websites can handle thousands of requests a second. But you've got to remember we're talking about web applications here. So we're not talking about static pages, which are just returning content. We're typically talking about, if we're attacking something interesting, then there's probably going to be a database behind it or other web services. So a lot of interactions will be going on. So 100 requests per second is actually pretty good. I think within web applications, we often see 10 requests a second or much less. And in fact, there's many cases where we've actually taken out web applications just by pointing Zap at them. So these figures are not that unreasonable. So, 20 minutes or a few hours doesn't sound too bad, but you've got to consider other things. We have both alpha and beta quality scan rules, and there are about 20 beta quality scan rules. Then headers. And so when you're attacking parameters, we're typically talking about URL and form-based parameters, but you can often find vulnerabilities in headers as well. So you've got to think about attacking headers and then path elements. So URL path elements, you can often attack individual ones of those to find vulnerabilities too. So this suddenly starts increasing the number of things you've got to attack. And then, of course, you've got things like high attack strength. So what happens if we ramp things up a little bit? In this case, I'm going to say we've got 20 pages in our example site, 5 parameters again, but 5 headers, 4 path elements. So we've kind of got 14 elements per page. So 2,800 parameter targets. We've got 20 core or release quality scan rules and the 40 beta ones and high strength. We're now up to over 4 million requests. And that means if you're getting 100 requests a second response time, that's 11.2 hours, or it's only 10 requests per second, we're talking of, nearly 5 days. And all of a sudden, this becomes a big problem. People won't want to use web application scanners or DAST tools if they take this length of time. People want results that they want really quickly. Now with Zap, we provide a lot of customization, but in the end, it all comes down to the number of requests and how long they can be processed. So that is our, one of the biggest problems we have when attacking web applications, and this will apply to fuzzers as well. So what can we do about this? Well, you make fewer requests, and that is kind of what we're doing with DAST tools. So when we have medium attack strength rather than high, we're making fewer requests, and we go to low rather than medium, we make fewer requests. And DAST tools try to do much more intelligent attacking. So we're trying to be a bit more like a manual pen tester rather than throwing loads and loads of data and different payloads at a web application. You can also do so, and that's the targeted request as well. So making sure you actually try and be more intelligent about these things. You can also understand the application structure better, and that's something I'll cover in a future slide. And obviously, speeding up your target system. If you get your target system running on a bigger box with more memory, so it responds quicker, then your scan times will improve. And you can live with it. You can accept, okay, if you want to attack an application a certain way, it'll take a certain amount of time. And I mention this here because it doesn't actually apply to quite a few of the other problems I'm going to cover. You just can't live with many of these. So let's move on, because that's not the only problem we have. Another big problem with web applications is discoverability. So when you're fuzzing functions or things, you typically have definitions available via the language. SAST, source code analysis, has access to all of the code. With web applications, we typically don't have those kind of definitions. We don't have a definition of the entire attack surface area. API definitions do exist, and they're great, but they're not always available. Unit tests are great, but they often don't exist when they're not complete. And with unit tests, what you can do, you can proxy those through your scanner, your DAS tool. We have crawlers and spiders, which can help, but these have limitations. So in ZAP, we have two different spiders. We have a traditional spider, which just looks at the HTML responses, finds links and follows them. So there's a traditional crawler, and it's very fast and it's very effective, but it doesn't work well with modern web applications. So modern web applications where the URLs, where the links are generated by JavaScript, you don't get those URLs in the HTML. So the traditional spider doesn't work very well with those, which is why we have the Ajax spider, and the Ajax spider launches browsers and clicks on elements. This can cope with modern web applications, but it is significantly slower. If you think we've got to actually launch a browser, we've got to wait for that page to render, we then go and click on something, got to wait to see what happens. It is much slower than the traditional spider. So solutions for discoverability, API definitions are obviously great for APIs. Sitemaps, if you can generate those from your application, they will definitely help. Comprehensive unit tests are really great, and they will help with the next problem as well. And using standard HTML controls so that crawlers can actually explore your application well. If you make your application hard for automated tools to explore, then you will be shooting yourself in the foot when it comes to security tools. So the next problem is good test data, and this kind of ties in with the discoverability. So if you imagine a register user form, so if you're a manual tester, whether a QA or penetration tester, you come across this form and you'll fill it in. And a scanner like ZAP will discover the form and will fill it in as well. And then you get an error message saying username must be an email address. Now, as a human, it's very easy to go, okay, right, I will now put test@test.com in. That's quite straightforward. That is much harder for an automated tool. Actually finding out where that there is an error message, there's been any problem parsing it, those things are just impractical. So an automated tool would typically not be able to fill this form in, and therefore it won't successfully create a user, and it won't open up a whole set of other functionality that could be available in the application once you've done that. That means that because you haven't filled in this form effectively, that means your automated tool will not be able to attack all that functionality. So solutions, as I said before, comprehensive unit tests. Unit tests are a great way of essentially teaching web security tools how the application is expected to be driven, and it allows the application to discover more content. Adding the attacks, we can do that. The tool knows all about the attacks. Getting good data, which is relevant to your application, is much harder, and unit tests are great for that. Tools like ZAP allow you to do manual configuration. So if you know there's a problem and you haven't got unit tests, you can configure ZAP to say this particular parameter needs to be an email address or anything else. But again, that's manual configuration. And that's one of the reasons why DAS tools can prove a bit tricky, because you've got to set them up right for every application. Next problem is understanding the web application structure. So DAS tools like ZAP build up an internal map of the application. And this is very important because this is how they actually attack the application. And if their map is not accurate, then they won't attack the application as effectively as possible. There are two different problems we can have here. One is that the application map can be too small. And it's TOO. I've only just noticed that. I'll have to correct that. So if your application map is too small, then the scanner will miss features. So how can that happen? Well, one reason is if you think about URLs, and a tool like ZAP will typically expect that the path elements of a URL will actually represent the site structure, and that the URL parameters will actually be data. And so if you have a parameter called page, then that will be typically considered to be data, and we won't attack it in the same way. So if you have things like page equals contact us, page equals login, we will only attack that particular URL with one of those values rather than treating it as a part of the site structure. That means that Zap doesn't understand it, and you'll have far too few pages, and Zap will not attack them all. Then we have a problem where parameters represent different actions. And again, it's a similar thing. So if you've got action equals add, action equals delete, by default, Zap will just attack the first one. It'll say action equals add, it'll attack everything else, and then it'll start attacking the action parameter. It won't attack all the other parameters with action equals add, and then attack all the other parameters with action equals delete, etc. So that's the problem where the application map is too small. Then we have a problem where the application map is too big. And the problem here is the scan will take much longer than it needs to. And this is typically caused by database-driven content. So if you think of those URL paths again, say if you've got company and team, and these aren't the actual elements of these are what is represented in the company, in the URL. So we'd have company equals, so we'd have Google, we'd have Microsoft, we'd have Stack.org, all these things in company, and then we'd have a set of teams. And if you have an application like that, then tools like Zap will typically treat these things as separate URLs. And that's a pain because this content is probably coming back from the database. So if you attack these pages with different company names and different team names, you're still actually attacking the same code. So attacking it 10 times, 100 times, 1,000 times, it doesn't make any difference. You're not getting any benefit at all. And of course, you have a problem with discoverability here. Say you have a calendar app. How long does it take to crawl a calendar app? Well, it's essentially infinite. You're not going to run out of years. So, your spidering could never finish if you don't put some sort of limits on it. So that's the kind of problem with understanding the web application structure. If you don't understand what that structure is, you'll either miss features or the scan will take much too long. Some of the solutions: auto detection is ideal. If your tool can detect these things, great, but that's really non-trivial. Manual configuration is usually the way to go. And again, that means you have to know about your application, you have to know how to configure your tool to handle it. Then authentication. This is a perennial bugbear for anyone who does any automated testing on web applications. There are so many different authentication mechanisms, and it's really hard to tell which one is in use, and even how to tell whether they're authenticated or not. Sometimes you can get, if you're dealing with an API, things might be easier. You might get a sane response code, HTTP response code, or at least some error message you can easily detect in the response. But when it comes to web applications aimed at humans, it's much harder to tell if you're authenticated, particularly if they handle unauthenticated users as well. So it's really hard to know whether you are authenticated and whether once you have been authenticated, whether you stop being authenticated. There are no standards around these things. They're all kind of application specific. And a lot of authentication mechanisms have anti-automation features, which of course are going to cause problems for automation tools. And don't get me started on single sign-on. That's just, it's a complete nightmare. It makes life really difficult. So some solutions: authentication tokens. If you can get a token which authenticates your tool and pass it to that, then that's a really good practical option. The other option is turn off your authentication or turn it down. Say you have an application that needs single sign-on on, but actually you have a configuration where you support simple form-based authentication. In your test environment where you're using your automated tools, use the form-based authentication version. Don't use single sign-on. It makes your life so much easier. Auto detection obviously is the ideal here if you don't have those options, but that proves very hard. And then we're back to manual configuration, which again is manual and is a pain. Then following on from that, we have session handling. Why is this a problem? Because if you don't maintain the session, then you've got to continually re-authenticate. And typically, once you've authenticated, if you try and attack something and you're not maintaining session, you'll be kicked back straight to the authentication page. You won't be able to make any attacks at all. So you actually have to maintain session. Now, this is a bit easier than authentication usually. So cookie-based stuff is fairly well known and fairly well handled, fairly straightforward. Client side can often be trickier. And then you've got a problem with logout links. So, you know, if you're exploring the application or if you're attacking things, if you hit the logout link, then you'll get logged out. And again, you've got to detect that. You've either got to avoid these links, avoid getting kicked off, or you've got to detect it and handle it. But there are also other session invalidating events. And that could be kind of like web application firewalls, or even that kind of web application firewall functionality built into applications. So when I was a web developer, I used to include traps. So traps are hidden fields, which you know the value of. Well, there can be a whole load of things, but in the case, I often put hidden fields in. And if that hidden field got changed, you would know it's an automated tool or somebody playing around with it, and you'd get kicked off. Or you'd start including logging, make more logging and alerts would go off, or whatever. But you know, if your application or you have a web application firewall that has these kind of features, then these can invalidate your session and potentially kick you off and not let you back in again. So those are complete pains. Solutions for these: auto detection for session handling is usually easier, but again, we just come back to manual configuration. And another thing, use standard mechanisms. If you kind of invent your own, then you're just asking for trouble. I could have put this in authentication as well, but I really hope people don't come up with their own authentication mechanisms in this day and age. And then finally, I think we've got issue detection. How do you know if you actually have a problem? So some issues are very visible in the web user interface. You get things like stack traces, reflected XSSs, all these kind of problems which are visible to a user or to an automated tool. Other ones are much harder. So blind SQL, you're kind of looking at timing issues there, out of band issues. So you're attacking remote services effectively, so you don't see any response via the web UI. And DAS tools typically can't see inside an application. So they might be causing all sorts of problems to the application, but if it's not visible via the interface that the DAS tools are actually driving, then you can't tell that it's very difficult to tell that there are real problems. So in this case, solutions, mostly down to the tool. There is some manual configuration as well. So often with error messages, you can put those into tools like ZAP. And you can do things like, you know, if you can do server-side detection, looking at logs, that will help. Then there's out-of-band application service testing. So this is where you set up a service that can receive HTTP, DNS, and other protocol queries when you make attacks, and then you see if that service actually detects it gets hit by pinged by these requests. And there's IAST, interactive app service testing as well. So this is where you're instrumenting the code, and then you can actually see what's going on. And that is going to give you a much better view of your application than just attacking it from the outside. So as a quick summary of all the kind of problems you have with attacking web applications, both via DAS tools and I'm afraid via fuzzers as well. If the time problem, it's going to take a long time. Discoverability, if you can't explore an application effectively, then you won't be able to attack all of it. Getting good test data, again, making it easy so you can actually discover more of the application. Understanding the web application structure, building that good map up inside your tool. Authentication, because if you can't authenticate, you can't get to the really juicy stuff. Session handling, because if you don't maintain session, then you actually you won't be able to attack anything. And finally, issue detection. How do you tell there actually are any real problems? And that's it. So that's everything from me. If you want to learn more about ZAP, then we've got a website, www.zaproxy.org, and you can follow ZAProxy on Twitter. And you want to learn more about the OpenSSF security tools, then have a look at openssf.org.
Thank you so much, Simon. That was an excellent introduction and a really fascinating insight into all the issues we have in web application security. So we are open to questions. You can join the Slack channel. So there's a link posted in the Click Meeting chat. If you're using the web app, it should just bring you right to the channel. If you're using the desktop app, you can click on the little plus icon next to channels and then type in the name Simon. You will see the channel and can join it there. Yes, I've gotten a number of questions as direct messages, but there was one actually in the channel, so we'll start with that one first, Simon, if I may. Max is asking, should those numbers be multiplied by 3 to 4 to DAST fuzz on Firefox, Chrome, and Safari, or is the goal to find conceptual bugs? And I believe that came up when you were showing all the kind of the numbers, how many requests you can send. Yeah, so they're asking, should these numbers be higher?
Sure, numbers could always be higher. So what we typically with DAST tools, we try and attack directly from the tool, like from Zap. So if we attack via the browser, it takes so much longer. So what we're really doing is we're typically proxying requests through Zap. So either manually proxying via your browser or using the Ajax Spider and proxying those requests through Zap. But we actually do the attacking from Zap. So this means things are much quicker. And we don't tend to do the browser-specific ones. We do have some, but we have much fewer. But if you actually want to explore the application via Chrome and Firefox and Safari, then the whole exploring thing will take longer. And in this particular case, I wasn't even including the exploring time. That was just pure attacking an application we already had 100 known pages for. But yeah, that will, it will definitely increase the time taken to explore.
Okay, then Tar is asking from Zap, can we do API fuzzing?
Yep. So as I mentioned in the talk, fuzzing, as far as Zap is concerned, is a manual process. So what you can do is you can highlight any part of any request, and then you can specify the payloads that you want to send to that particular target. And you select multiple targets and multiple different requests. So you can do sort of pre and post processing, all those things, but it's very much a manual process. So yes, you can do that on any request, whether it's an API one or not. When it comes to actually DAST scanning, then yes, Zap does DAST scanning or web scanning on APIs. We support the OpenAPI Swagger definition. We support SOAP, and we support GraphQL as well.
Okay.
So we've actually got a Docker image, and we have a package scan, which is just focused on API scanning as well.
Okay, so there are lots of questions coming in, so I'm going to try and pick out some. Benaz is asking, apart from performance, what are the other issues with the Ajax Spider? Is it able to get good coverage on framework-based apps such as React apps?
It depends what features you use. And one thing it's worth pointing out is the Zap core team, we don't get a huge amount of feedback. So you don't have to tell us when you download Zap, you don't have to tell us when you use Zap. We know Zap is used really heavily all around the world, but we don't actually get a lot of people telling us what they're using it for, what problems they hit. We get some problems reported to us, but it's very difficult for us to know how effective these things are. We don't see the results. So, we know there are some apps where it gets good coverage and some apps where it's not so good. And at the moment, we don't have enough data to tell us, which ones of those are. And, even if we had instrumentation or whatever in Zap, we still wouldn't know anything about the target application, how effective it is. So we're kind of very reliant on feedback from people, and we don't get enough. So more feedback, please.
Okay, so you have a great audience here who I'm sure will all be trying out and giving you feedback, maybe more than you can cope with. So
we can cope with a lot of feedback, don't worry.
Okay, so then some questions which came over direct message. What are the most typical and most critical bugs you find?
Well, so there are, tools like Zap are good at finding particular types of vulnerabilities. So the injection ones, so your cross-site scripting, your SQL injection, those type of things. If you're using Zap manually, then it's very different. And I think, this is one thing where, just using automated tools is not the solution, particularly with web applications, because with web applications, the really fun ones, when you're attacking the application logic, and that needs a human brain. You need to understand what the application is trying to do and then subvert it some way. So a classic case could be if you've got a shop and you have, you've got a basket, and you find out that you can attack, you can change the requests, and you can put a negative amount in. So you put -100 of this particular item, and all of a sudden the shop owes you money. Now, an automated tool, it can put minus a negative amount in, but it doesn't know that we're talking about a shop. It doesn't know we're talking about money. It doesn't know that we can actually, you getting money off the shop is a bad thing. So attacking the logic, you really need to, until we've got really good artificial intelligence, which we don't have, you need that human brain. And tools like Zap are really great for allowing pen testers to get on to see what's going on, but you need that brain to kind of understand things. So the really fun ones, I think, are the ones you find manually using tools like Zap. But yeah, the injection ones are kind of classic ones for DAS tools to find automatically.
Okay, actually, there's a follow-up question which leads on very nicely from that. Are the types of bugs you find changing over time, or are they the same bugs coming up again and again?
Feedback. Again, we don't know what bugs Zap is finding. We would love to know more. So
well, then
yeah.
let me rephrase the question. Have you had to update Zap a lot to find new classes of bugs, or are you more kind of improving the ones you already have?
Well, I think modern web applications have had a lot of complications because you've got a lot more functionality in the browser, and that makes things much harder as far as traditional security tools are concerned. So that's something we need to improve. Yeah, I think over time, particularly when I was at Mozilla, when we were looking at things like the bug bounty and bugs we were finding, the traditional ones are becoming less. It will depend on the applications and the experience of your developers and whether you're using automated security tools or not. So it's, I don't have that kind of wide view of all the applications that are across a lot of companies. But I think the experience I've had that, developers are learning more about security. We're not seeing some of the simple stuff anymore. It is getting harder for security tools, and that's a good thing.
That's excellent, yeah. Okay, looking at the time, we have time for one last quick question. Thurm asks, can Zap leverage unit tests in the form of automatic test scripts from Selenium or Appium?
So the best thing to do is proxy those through Zap. So if you can proxy your unit tests, proxy them through Zap, that essentially teaches Zap about your application. It teaches about the structure. It teaches about good, useful test data for exploring things. That's an ideal approach as far as I'm concerned.
Excellent. Well, Simon, thank you so very much for that excellent talk and all your answers. So community, please give Simon feedback on what you're doing with Zap. And if you want to hear more of that, you can follow him on Twitter at Sinon. I hope I'm pronouncing that correctly.
Yeah.
I'll spell it out for you. It's at PSIINON. So PSIINON. You can follow him on Twitter if you want to hear more. Okay, so thank you, Simon.
Thank you very much.
Now let's move on to our next talk. Before I go to that, actually a quick announcement. Make sure you confirm in the email you get if you want to receive the recordings. So if you want to, we're going to share all the videos and all the slides. And the email you got should contain a link with which you can confirm that you'd like to get those things. So you can do that now. Okay. Next up, we have Marina Polyshuk, a research software engineer at Microsoft Research. She's passionate about systematic testing complex software as well as teaching engineering best practices. Over the past 15 years, she's created testing tools for the Visual C++ compiler and the SQL Server database engine. She's currently working at Microsoft Research on the problem of how to find security and reliability bugs in cloud services through fuzzing their REST APIs. Before Microsoft, Marina got her master Computer Science from the University of Wisconsin-Madison and her Bachelor in Math and Computer Science from the University of Michigan. So, Marina, great to have you here. I'm really looking to your talk on stateful REST API fuzzing. So, the mic is yours.
Great to be here. Thanks, Matthew. Can you hear me okay?
I can hear you fine and I can see your slides. Everything looks good.
Perfect. So, my name is Marina. I'm from Microsoft Research, and today I'm going to talk about a tool that we've built based on some research we've done on REST API fuzzing. So this talk is going to be all about APIs. All right, so how important is it to fuzz REST APIs? Well, as all of you know, web APIs are everywhere right now, and in particular, there's been huge growth in the past few years of public APIs that's officially tracked, but then also microservices architectures have gotten very popular. So there are lots of private APIs, and there's an increased attack surface on all of those fronts. Moreover, all of these services are rapidly evolving. So the matrix of different versions constantly being added, new features, as well as things have to be patched in production occasionally very quickly. This all, again, kind of increases the risk that something will go wrong, and you need testing to keep up with that rapid pace of development and deployment. So the question we ask ourselves is how secure and reliable are the APIs, and how can fuzzing help? So this is going to be the outline of my talk. I'll motivate why do stateful REST API fuzzing? What does that mean? How can that help you get good results with fuzzing? I'll talk a bit about Wrestler, which is a tool that automates stateful REST API fuzzing. I'll talk most of the time about the type of bugs that Wrestler can find, a bit about CI/CD, and some future work we have planned. So Wrestler actually came about as a project mainly motivated by Microsoft internal feedback on having applied some techniques and having some issues that they wanted us to take a look at. So we started researching this problem in 2017. And some of the things that we saw that people were trying is, one is just either manually or loading up an API specification and fuzzing each request in isolation. And so if you do that, just automating that will have pretty low coverage. So you need a human in the loop to really guide the fuzzer and make sure that it's covering what you intended to. There are also many ways that you can do traffic capture and replay with fuzzing, and this is pretty standard. But of course, the coverage is going to depend on what your traffic is, whether it's from live traffic or from your unit tests. So again, you really need quite an investment there. And then for high-value targets, people, of course, were manually writing fuzzers. So all of these solutions, they can work very well, but the problem is they were not really scaling to large, rapidly evolving REST APIs, such as, for example, for Azure services. And also, there were some important bugs that these missed, and we'll go into it in the rest of the talk. So here's an example bug. So if you look at this for just a few seconds, see if you can spot what the bug is here. So there's a client. It's first creating a resource of type CM, and it's named X. It has a value, so red here indicates that it's invalid, so it's actually a fuzzed data value. And it's creating it in some region, US West. And there's a 500 internal server error. And that's already kind of a bug indication that something went wrong, but let's see how much further we can take this. So you get all these resources of type CM, and you don't have any. Well, okay, I got an error. Everything seems fine. But then what if you try to create that same resource now with a valid value and in a different region? I should be able to create that resource, right? Well, in this case, we weren't able to create the resource, and we got a conflict. So what happened after some manual investigation, we found that X is now a zombie resource, and moreover, it wasn't counted against the user's quota. So an attacker can just keep creating these resources very quickly with different names, and potentially there could be a DOS here, both in terms of an actual resource on the backend that's not getting cleaned up, Or in some cases, like just the domain of names can be finite and not that large, and you can prevent users from creating like any resources of type CM. So what you should take away from this is that to find this bug, you need both invalid inputs, valid inputs, and this carefully crafted kind of sequence of requests. And this is precisely what we were trying to target with Wrestler and with our fuzzing algorithm that we've developed. So Wrestler is stateful. So what does that mean? All the tests in Wrestler are sequences of requests. And we only fuzz a request if all of the prerequisite resources can be created. So we found that this really provides much deeper coverage than if you try all the requests, regardless of whether prerequisites are available. And the fuzzing algorithm also works hard to avoid redundant testing. So I won't have a lot of time to go into that, but you can refer to some of the Wrestler papers for the details. It's automatic. So here today we require an Swagger OpenAPI specification. We found that internally at Microsoft, as well as talking to our users since we've open sourced the tool, a lot of the large kind of public cloud services do use OpenAPI specifications because they use those to generate client SDKs. So this is something that developers kind of already maintain as part of their existing workflow. And this is great because when we plug into that workflow, we can both find bugs in those specifications as well as actually get a pretty good, reliable artifact for fuzzing. And what Wrestler can do today is it can provide, using those specifications, good coverage out of the box if the specification has enough details. And Wrestler is also extensible. So in addition to catching things like 500 errors, it allows you to write your own security checkers and plug into the fuzzing loop. So how does it work? It takes an OpenAPI specification, and the first step that it executes is it compiles it. It infers each request type, which is basically taking the full schema and figuring out what are the inputs and the outputs of that, and then identifying producer-consumer dependencies. So this means one request produces a resource, what other requests actually need that resource as an input. And it also has code to parse responses. In the second step, the test engine, which is actually what's generating and executing the tests, it takes the grammar, it runs the service, and it executes requests against the service, and it analyzes test results. And one thing that it does to prune the state space is it has a feedback loop to learn from past service responses and avoid duplicates. So if you've already tested, for example, the sequence A/B, and you got both 400 error codes for A and B, you're not going to try A and B in a certain context until maybe you've moved on and maybe you can find a bug that you couldn't earlier. And it's doing a systematic state space search. So it's really is trying to find all the sequences and all the combinations of parameters while being as efficient as possible. Here's an example. So you have a simple blog service here, and the compiler will produce a grammar. This is an abbreviated form of the grammar. If you're interested, I encourage you to go on GitHub and try out like the demo, which is basically this service here, and look at the grammar more closely. It basically describes the schema of the request, parsing out of the response what it needs, and the dependencies, which is the ID here. So then the Wrestler test engine takes that grammar, and what you see in the output, this is just a standard kind of HTTP request that it's sending. It's not doing anything more fancy than that. So in particular, Wrestler is a black box fuzzer, so it doesn't expect any kind of instrumentation to be available. All it's using for feedback is the responses. Here's a typical fuzzing session. So there are a few interesting things here. One is look how many positive status codes there are. So this is, again, kind of what differentiates Wrestler as a fuzzer, is it's really trying to first execute kind of a positive scenario, really get deep inside the application, and then do fuzzing. And another thing that's notable about the fuzzing session is that each time you go deeper into the search, which means you increase the sequence length, we actually found for this blog application, which we were able to instrument, that coverage did increase with each sequence length up to length 3. This is a very simple service. So the sequences here, what this means is the first sequence is just trying each request in isolation, but only if it has all the prerequisites. And then in this sequence of length 2, you're able to now get a little bit further because you've created a blog post and now you're able to read it and to delete it. And likewise for sequence length 3. So what are the type of bugs that Wrestler can find? You already saw one earlier that I presented. Our first case study was GitLab. So GitLab is a pretty complex service, about 300 request types. And we found 28 new bugs. And this was just looking for 500 internal server error codes. This was our initial case study. And an example of bug is you create a project, you create a repo with a proper valid commit, and then you delete the repo file with an empty commit message. So, we expected that to all be valid, but instead we got a 500 internal server error. And all of these bugs have been fixed. You can read more about it in this paper, Stateful REST API Fuzzing from ICSI 2019. A more recent study we did was on a few Azure services. So I'll just talk about one here in the interest of time, Azure DNS. And here we actually developed a specific new algorithm for JSON payload fuzzing that also has a feedback loop, and in particular, it dynamically learns and augments the set of possible inputs using past responses. So for those of you who've worked with APIs a lot, you know that sometimes you can create a resource with just one parameter, and the schema has like 1,000 parameters. But then what the data that you actually get back is you may get all 1,000 of those parameters initialized with whatever the defaults are in the system. And so this can be very interesting to then fuzz those values. So in the DNS service, it has 13 request types. Many of them, however, have a very large schema. So this 65 schema elements and like lots of enum values. So the state space is actually pretty large. And here we used error code and message as a signal of coverage. So this also has some coverage guided kind of element in this algorithm. And we actually found new 500 server errors in all of these, all but one of these requests. And the last one only had 2 schema elements, so it wasn't very interesting. And after deduping everything, there were 7 new bugs filed. Again, you can read in more detail about the bugs in this paper from FSC 2020. All right, so to talk a bit more about classes of bugs found by Wrestler. So the interesting thing is if you use the tool, like any tool, sometimes you're going to find these bugs automatically. Sometimes when you're actually investigating, hey, what is wrong here? I'm trying something, it's not working. Is the tool not working? After some more investigation, you can possibly find some more bugs in the service. And then we actually had a few bugs that were found by service alerts by running Wrestler, which are bugs that Wrestler isn't designed to try to find, but in the course of it running, it kind of triggered something going wrong in the service. And I'll talk a bit about those. So one use case for Wrestler is actually validating the API specification. We make use of examples to try to help with the initial coverage, initial positive coverage. And if the specification is either under-documented or inconsistent, Wrestler basically won't work well out of the box. And during that investigation, you'll find either you can work around that by using Wrestler, or you can actually fix those specifications. Of course, one of the biggest classes of bugs is input validation. And today, the main test oracle for that is getting 500 server errors instead of an expected 400. So we found a few bugs in authentication. We have some specific checkers for testing whether you can access another user's resources that you shouldn't. But also you can just try Wrestler with an invalid token across a large API. And if it runs and you see in the course of it some 200s, that's a sign that something might be going wrong. You might have an unauthenticated API bug. And then we also had one pretty interesting bug where we ran Wrestler, and it was fine in kind of its quick fuzzing mode that it has. And then when we went to full fuzzing, it kept crashing. It kept just disconnecting from the service at a particular point. So we're like, why is this happening? And it turned out that there was actually a bug that turned out to be a design bug in the API, where a particular value was corrupting the authentication code path and was just causing the service to be invalid. So these bugs do happen. These kind of more severe bugs. Similarly, like resource exhaustion is one that we've seen where just by running Wrestler, it's not able to detect those bugs because they're on the back end and it's completely black box, but it can cause issues that are caught by service alerts and service incidents. And then you already saw some examples of resource management issues in the first bug that I showed. Similarly, data leaks. Today, Wrestler doesn't have an automated way for you to try to find data leaks, but just by looking at the logs, you can discover them. So we found one that I wanted to call out here. And the really encouraging thing is we've actually been tracking the bugs that we reported both internally and a few in the open source in the GitLab project, and all of these bugs are being fixed. So even when they're not necessarily security critical, people see the potential for them to cause issues later down the line, or sometimes they're just user experience bugs and they're very willing to fix them. And of course, in terms of scenarios for where to run Wrestler, careful when running it in production because it has some of these severe bugs that can happen. Instead, think about if you're able to run REST API fuzzing during development, or CI/CD regression fuzzing is becoming very popular for kind of traditional binary fuzzing. But of course, a big problem with putting things in CI/CD is the time and the complexity of having a reliable test environment in CI/CD that isn't going to be breaking your builds all the time. So one kind of happy medium that we've seen some people adopt is doing Wrestler testing during deployment validation. So where you already have some test environment that is good enough for you to do other integration testing, maybe also running some fuzzing would be safe there. Wrestler does try to clean up after itself, as much as it's able to based on the knowledge that it has. And then also, if you're looking to bug hunt for specific classes of bugs, you can either use the existing checkers that it has or tweak them a bit if you're looking for some kind of specific authentication code path that isn't covered by the out-of-the-box checker. The code is out there, so you can definitely extend it pretty easily. So to talk a bit about CI/CD, so a big element of CI/CD is scale. And you may already have your own CI/CD system at your company. We've developed one specifically for REST API fuzzing. So I'll talk a little bit about that. This is a tool called Raft. And Raft is a self-hosted REST API fuzzing as a service platform. So what it does for you is it can run a variety of tools already, including Wrestler and Zap, and it's easy to onboard new tools. And it basically spins up a bunch of Docker containers and can trigger off of your build and give you bug notifications back that you can use in your day-to-day CI/CD. And for more details, you can see this link. So here's kind of roughly the workflow. So you push code, and when you start a Raft job, it basically the configuration is something that you already have checked into your repo, so it doesn't require a lot of kind of reconfiguring based on the changes in your API. You just still need to provide that open API specification. And through working with various teams at Microsoft, we've added some features that you may care about, like secret management and VNet support. And also you can use it in your local testing. One scenario that you may want to run is it's good at launching a bunch of different tools in parallel. So if you want to kind of stress the system a bit more, you can do that with Raft. So in terms of challenges and future work, so one thing we're really driving toward is better coverage out of the box. So if your service is pretty simple, maybe the Open API spec has enough detail to get 100% coverage. Otherwise, some initial configuration is required. So today, we use examples that are provided with the specification. we want to improve how we handle that. There's just implementation limitations, but also being able to mine a lot more valid values from examples, as well as search for valid data payloads using those values in the algorithm to try to get the initial coverage to be higher. Likewise, this algorithm to infer producer-consumer dependencies, so understanding what resources a particular API produces that then are required as inputs to other APIs. We want to improve those detections. We're working on supporting CI/CD as well as regression fuzzing. And finally, a few people in the community have reached out on their scenarios for security checkers that we didn't cover. So we're really excited to hear more about this. This is definitely an area where we can do a lot more. And so if you're interested, or you've already implemented a new checker and you would like to integrate it or just share your results, please talk to us on GitHub. We're looking closely at that right now. All right, and this concludes my talk. So APIs are everywhere. They're a rapidly growing attack surface, and hopefully I've convinced you that REST API fuzzing is important, and stateful REST API fuzzing can help you get deeper API coverage. But as is evident, thoroughly fuzzing services with a large or complex API is a very hard problem. Automated tools like Restler can help, and there's definitely more improvements that are possible. So in conclusion, thanks for coming to my talk, and please try out Restler and Raft and give us your feedback. Thanks.
Thank you. Thank you, Marina, so much for your talk. And I can only echo that call. Please do go out and try these tools. Your apps will be better for it. So we've got lots of questions coming in. I hope we can squeeze them all in. I'll bundle a couple of them around coverage. You were talking about, on the second to last slide, that you wanted to improve coverage out of the box. Could you maybe talk a little bit more about how you're planning to do that, and if code coverage as in a non-black box approach is something on your roadmap?
Yeah, so today, kind of the immediate next step is being able to better take advantage of example payloads, such as from traffic, such as from the OpenAPI specification provided to the user. So as an example, Restler today takes all of the example values that it has and kind of uses it as a set. So it just has, for this parameter, there's 5 values, this other parameter, there are 10 values. It doesn't actually treat those as a holistic, like this was a full request that was sent. So, that improvement is probably the first one that we would do. Further down the line, also, the algorithm today, again, doesn't have, it kind of explores the space of all the inputs using a uniform approach. It doesn't have something specific to try to raise coverage versus to try to find bugs. And then as far as the incorporating instrumentation, so this is a scenario we've talked about for a long time. Some of the services that we've been dealing with, this would be pretty kind of difficult to determine, like, what do you instrument, because the system is very large. But I think it's definitely something that could be done in terms of incorporating some signal like that into Restler. So talk to us on GitHub if you have ideas, but I think that one is probably a bit further out. We're not going to immediately focus on that like in the next few months.
Yeah, I understand that. So actually, there's a good follow-up question to that. Are you actually using Restler against Microsoft products like Office 365 or Azure APIs and stuff like that?
Yeah, so it's been applied, and I think it was on the slide, but I forgot to mention this. So it's been applied to various products in Office 365, Azure, and Bing over the years. And I would say, like, there's a variety of levels of maturity where people are applying. Some of it is just like engineers trying it out and finding bugs. Some of it is, people are setting up to run it in CI/CD. So yes, it's been applied, and there's actually quite a bit of detail in the two papers that I mentioned. One is from ICST 2020, and one is this recent FSC paper, FSC 2020, where you can read more about some of those case studies.
Okay, excellent. And then we have one maybe more technical question. I hope that you'll be able to locate what exactly they're asking. The question is from media asking, how do you construct the tree? Is it based on REST dependency from the Open API? I think that was from near the beginning of your talk.
Yes, so that's correct. It's based on the dependencies plus trying all the combinations of the request types. So for example, if you have request types A, B, and C, you're actually going to try AA, AB, BA, etc. But only if they don't have any dependencies. If A is required to be run before B, then you're not going to have BA. So hopefully that's like a very simple explanation. Our first paper has a lot more on different algorithms that we've compared to determine which one works best.
Do you have a web page or a social media account where I can point people where they can find your papers?
They're actually all linked off of our GitHub project page.
Okay, excellent. So folk who want more technical detail, go to the GitHub page. Reading papers is really interesting. Okay. Oh, then one more question which came in is, how do you internally, or how do you evaluate Wrestler internally? So how do you measure when you're improving, whether you're improving things or not?
Okay, great. So there's two main metrics that we use, and then we have metrics for specific features of Wrestler. So the two main metrics are how good is the coverage for the APIs out of the box. So there's actually a special mode of Wrestler called test mode that all it's doing is it's trying to quickly run the minimum number of tests to exercise the entire API and see what is the positive coverage. So this is much more like just functional testing of the API. So we measure that by, we have a bunch of services where we know we've had trouble in the past, and we essentially have a coverage number that we collect after we do major features, and we see whether it's improved or not. And then the other is effectiveness, by the number and type of bugs we find. So this is something we look at where sometimes Wrestler finds these bugs, we report them, and then we can't always tell how severe the bug is. So often, we look for feedback. Also, we look for feedback of, hey, this bug wasn't flagged by Wrestler, but when I looked in the logs, I saw that this bug was happening. Will you incorporate it so it's actually able to report it?
Okay, thank you so much. Okay, sadly, we are out of time, so let me thank you again for the wonderful talk. And that was a great insight into how Wrestler works, and I'm looking forward to see what you do with it in the future.
Thanks a lot.
Okay, next up, Fuzz Everything, our battle cry. Actually, this is a double-barrel talk. We have Abhishek, a principal software engineer from Google, and Fabian, a senior software engineer at Code Intelligence, who'll be telling us a bit about how we can fuzz everything. So the mic is yours.
Abhishek, I think you're still muted. Do you want to go first?
Can you guys see me?
Yeah, we can hear you.
Cool. So let's get started. So this talk is about fuzzing everything in open source with OSS Fuzz. And also we will be talking about our recent collaboration with Code Intelligence on Java fuzzing. So first, a little bit background about us. So I'm Abhishek. I work at Google, and we started the OSS Fuzz project like 4 years back. And that was in response to the Heartbleed vulnerability. If you remember Heartbleed, that impacted like OpenSSL servers all across the globe and was really an eye-opener for the security community. And now I manage our new Google open source security team. We have like a pretty broad mission to improve open source security at scale. So if you want to learn more, there is a recent blog post on Google security blog called the KPF framework. So definitely check it out. And we have Fabian with us. Fabian, you want to introduce yourself?
Hey, yeah, I'm Fabian. I'm a software engineer at Code Intelligence. I myself in my free time maintain a few security-related OSS projects and also contribute to the Chromium project.
Cool. So first, let's talk about OSS Fuzz. For folks that don't know about it, it's a free fuzzing service for the open source community. And we had three major goals when we started this service. The first goal was actually to find all the security vulnerabilities and your stability or functional bugs at scale. So, and also using like really modern fuzzing techniques. So to give you an example, like the latest and very efficient fuzzing engines like AFL++, libfuzzer, HongFuzz are all supported in this service. The second goal we had was to make this platform really simple to use for open source developers. And we really encourage them to do these integrations with the service. So not the security team members, but actual project developers. And we also reward those integrations. And the third goal we had was not just finding security bugs, but also to get them fixed. So if you want to look at some of the OSS Fuzz numbers, we have a pretty high fix rate of 90%. And that's all possible because of the smooth workflow we created that even works for the most resource-constrained developers. So a little bit on the history of OSS Fuzz. I already told you we started it 4 years back. We started out pretty small, like we had support for only C, C++ projects. And we started with a bunch of sample projects like OpenSSL, libxml2, etc. Then after 6 months, to increase adoption of the service, we encouraged the open source developers to do these integrations, and we would reward them like up to $20,000 to make those things easier. Then in early 2019, many of these developers were asking us about the backend infrastructure that powers OSS Fuzz, so we open sourced that as well. That's ClusterFuzz. They really helped us with good feature requests, gave us some good PRs to add new features. Then later in 2019, we started expanding the scope of OSS Fuzz to incorporate new languages like Golang and Rustlang support were added there. Then in early 2020, like in March, we really realized that many of the fuzzing research papers that were coming out every year, we were not able to evaluate them in industry use. And that's where we started FuzzBench as a service, which allowed the community fuzzing research to be evaluated at scale. So you can run, let's say, like 5,000 core experiments and get your results back in 24 hours. So I think this proved out to be useful. Like if you think of AFL++, that kind of graduated out of regular experimentation from FuzzBench. So we feel like we served a purpose there. And then finally, recently we started collaborating with Code Intelligence folks on adding Java fuzzing support. So Fabian will go next on it. So let's talk about like usual fuzzing workflow, like how fuzzing looked like in past. So usually fuzzing would be a set of very tedious tasks that would be pursued by, let's say, members in a security team. They would first try to learn, they would spend a couple of days learning the build system and the underlying program APIs. And then they would start writing the first targets in those. They would try to create these builds manually with different memory instrumentation tools like sanitizers. Then they will decide to run some of these fuzzers at scale, like either on their like local beefy machines or in the cloud. But a lot of these steps were very manual. Like analysis of these crashes was very painful, and like the deduplication would be very rudimentary. So then they would file these crashes manually, and even after developer would fix these things, the verification was either manual or some of the folks might completely skip it. And the final part, even if the vulnerability gets fixed upstream in the OSS repo, consumers would find it pretty hard to uptake those fixes. And the reason being that OSS developers are very resource constrained. Like they might not even bother with like filing for the complicated CVE process. So in a way, taking those fixed vulnerabilities would be hard. So we have really worked on trying to simplify this fuzzing workflow. So first thing is we encourage the actual developers to integrate fuzzing in their projects. So that saves quite a bit of time. Like in usual cases, we have seen like a developer spending roughly a day to write like a fuzzer unit test and the related integration files. And this could be easily done in less than 100 lines of code. And rest of the workflow, we have tried to automate it completely. So to give you an example, for OSS Fuzz, it will automatically create the right builds with all these memory instrumentation tools like sanitizers, and also hook into the available fuzzing engines. It will run these fuzz targets at massive scale. It will automatically analyze all these crashes, deduplicate them, and file them automatically. It will CC the developers in an automated fashion as well. And once a developer fixes those issues, they will actually verify the vulnerability as well. And in case, like if the developer didn't fix it properly, they will get a notification to fix it. So that's the automation from OSS Fuzz. And then we recently announced a new service called OSV, which tries to make uptaking vulnerability fixes much easier. So we are encouraging the community towards capturing more precise vulnerability data, where you will exactly capture like the right regression and fix commits. And in that way, it can easily hook into your vulnerability management systems. So OSS Fuzz has been serving the open source community for a while now, and we have some great results and impact to come out of it. So right now, more than 400 open source projects are integrated in the OSS Fuzz service and are getting continuously fuzzed. So think of your popular critical open source library, like let's say curl, TensorFlow, Kubernetes, OpenSSL, etc., are all getting fuzzed through OSS Fuzz. Till date, we have found 6,000 security vulnerabilities. These are all unique vulnerabilities we've found so far, and also like 22,000 functional bugs. Last year, we also massively scaled our infrastructure. So now it's running on a scale of 100K CPU cores. So this is really helping the fuzzing for projects, because every project is guaranteed to get at least a few hundred cores. And we uncover most vulnerabilities pretty quickly, so they don't even make up to the stable branches at all. So now we will be going over our collaboration with Code Intelligence folks. So I would let Fabian take over and go over that.
Thank you, Abhishek. Now I'm taking over. And as you've heard from Abhishek, until very recently, Java was a notable omission in the list of languages that OSS was supported. This has changed in, this early March, when the newly released Jessa fuzzer, produced by Code Intelligence and open source on GitHub below, which was only open sourced in February, so this is also a very recent addition, came out. And what is this fuzzer? It's based on proven tools like the libfuzzer fuzzing engine and Jacoco for coverage instrumentation. It's coverage guided, like all modern fuzzers are. It's in process, which means that in the same process that your fuzzer runs, your Java virtual machine will execute your Java target. So this is actually really fast. Like you get 1 million executions per second on an empty target, and still maybe 100,000 executions on a realistic target. And the good thing is that you instrument bytecode directly. So you don't need source code, and this will be directly compatible with your Kotlin Scala Clojure application. So what makes Jesser a good fuzzer? It takes all the tried and tested libfuzzer features and ports them to Java. So for example, you get automated minimization with deduplication, and this also works on clusterfuzz. You can fuzz in parallel. You have a value profile that allows you to break complicated checks into smaller steps and make the fuzzer progress better. And it has also some additional Java smarts. For example, you get pure Java reproducers that you can share with maintainers. You have a keep going mode to skip very uninteresting null pointer exceptions in favor of the more interesting bugs. And you have an elaborate method hooking framework with which you can implement your own Java equivalents of the C++ sanitizers. So let's look into what Jesser can do, or what a Jesser fuzz target looks like. So this is an example fuzzer with 2 helper functions that perform things that you can often see in apps or web apps that are sometimes a bit broken. For example, here you can see base 64 encoding, takes a byte array, turns it into a base 64 string, and a very, very insecure XOR-based encrypt function with a static key. And then further down, you have a fuzz target. A Jesser fuzz target is just a static fuzzer test one input function that takes a fuzz data provider. That's a Java object that provides you convenience functions to create useful primitive Java types from the raw fuzzer input. And then it does some, basically magic compares. So it takes some bytes from the fuzzer input, converts them to base 64, and compares them to some magic value. And it does the same thing for the result of this insecure encrypt, and then compares them with very large magic long values. And then in the end, if the fuzzer has passed all these checks, it will lead to an uncaught exception, which will be reported as a crash. And as it turns out, if you run Jesser, it only takes about 5 seconds to crash this target. So this is how you would invoke Jesser on this target. And you can see that after about 2.5 million runs, with over 600,000 runs per second, it has crashed the application. It has produced the illegal state exception. And you can see further down that the crashing input is Jesser value profiling. So using this feature, you can actually get into even complicated fuzz targets pretty quickly. You can also see some of the additional features here, like Java reproducers and the dedup token for deduplication. So we have a capable fuzzer, but what do we do with it? You could say Java is safe. I mean, it is memory safe, and it's also pretty safe in other senses. So why should you fuzz Java? Well, first of all, even Java applications have functional bugs. You can have uncaught exceptions that crash your services or applications. You can have assertions in there that you thought would never, not hold, but in fact, sometimes that can happen. Or you can just have multiple implementations or libraries that cover the same use case, but still produce incorrect results, as in different results for the same input. But then there are also potential security issues. Easy to detect are infinite loops and out-of-memory errors, which could result in very efficient denial of service attacks. But then there's also cross-site scripting in the context of web applications, for example, in sanitizers that are Java-based or HTML frameworks, or even remote code execution. So for example, if you deserialize untrusted Java objects, or if you run Jakarta with an expression language, you can actually get remote code execution in the supportedly safe Java language. And all these can be found via fuzzing. So now that we've seen this, let's look into some real bugs that Jesser has found. So in this part, we'll look at the JSON sanitizer, which is an OWASP Java library that you can feed arbitrary bytes and strings into, and it guarantees that the output is always valid JSON. Even more than that, it guarantees that the output will never contain certain substrings that, due to the weird nature in which HTML is parsed, might mess up your scripts if you include the output of this thing verbatim into your script blocks. So you can take untrusted data, that's the claim, you can run it through the JSON sanitizer, and the output should be safe to be embedded right in a script block in your HTML, like below in the orange box. Well, what did we do? We set this up with some kind of a property-based fuzzing approach in Jesser. So this is the fuzz target. We're just consuming a string. We're passing it through the sanitizer. We're catching any exceptions because that's not what we're interested in right here. We also found some undeclared ones. And then we're asserting that the safe JSON that comes out of this does not contain this substring. Because if it does, we could get cross-site scripting. And you can probably tell, I mean, I wouldn't be telling you this if we wouldn't have found a bug. So we found a bypass of the JSON sanitizer. It's actually not that hard if you use JSON escaping in a smart way, namely you escape the first letter of an HTML tag in your JSON string. You can pass it through the sanitizer and it will output the original tag. So what you can do is that you can take the string up there, you can pass it through the sanitizer, it will end up in the HTML that I showed you before, but there, because of the nature of HTML, this closing script tag in a JavaScript string will actually close the script block. You start a new one, you insert an alert, and you get cross-site scripting. So this is an example of a high-severity security vulnerability in a Java project that you can find with fuzzing. And there are more. We can look at this code snippet, which is a utility function, IO utility function in a popular library. And it's supposed to read a buffer up to a certain length and consume it fully. And what does it do? Well, it initializes a buffer to read into, and then it starts a loop. And it calls a read method. We don't know what this is, but it calls a read method. And it tries to read as many bytes as it still needs to read length bytes in total. So what could possibly go wrong with this method? Well, what does the read method return if there is not any data anymore? It turns out that in this case, it didn't return an error or something like -1. It just returned 0. So that means that you call yourself up in an infinite loop if the buffer contains less than length many bytes. And this actually led to an infinite loop in Apache PDF box on a stable branch, got a CVE assigned. And this is a bug that, for example, you could abuse in the context of a web application that accepts some PDF, for example, to parse out some text from it. With just a 500-byte PDF, you could consume many resources on that server and potentially crash it or just denial of service completely with very little effort. And there's the fuzz target that uncovered this bug. It's very simple. As Abhishek said, these fuzz targets are usually pretty short. So here, it's just, I think 6 lines of code. You just load a PDF from the raw input data of that the fuzzer provided you with. You set a memory limit. You catch the exceptions that this thing declares, and then you let it run. And it will find this bug pretty quickly. But you could say, okay, this is not very interesting. I mean, every fuzzer should find bugs where some size, some length is not as claimed. But Jesser can do more. So we also found an infinite loop in Apache Commons Compress. This has no CVE because this was on a branch which was close to being released, but luckily hadn't been released yet. Here, the fuzz target is even shorter. And what went wrong? Well, in Apache Commons Compress, a tar file allowed negative sizes for files to be claimed in the file metadata. But then Jesser pretty quickly produced a tar file with a file entry whose metadata claimed that the file had a size of minus the length of the metadata, which was 512 bytes. So that meant that after Apache Commons Compress had parsed the metadata, it would set out to parse the file contents, which meant going back right to the start of the metadata. So it would now encounter, on the next loop through the parser, it would encounter a new file entry. It would parse it again, go back, and so on ad infinitum. And that, well, gives you the lovely side of a Java out-of-memory error caused by an infinite loop. This was also a 500-byte tar file that's easy to produce, easy to upload, will be accepted anywhere, and can potentially crash your server, or even worse. So these were just 3 examples of the things we found with Jesser by ourselves or on OSS Fuzz. And in total, since Jesser's release in mid-February this year, we found over 50 bugs in over 15 open source projects that we've fuzzed, and we haven't really fuzzed all the projects that we can think of yet. In those, we found 8 security issues, 5 of which have been part of stable or other released versions of software. So these have been assigned CVEs. All have been fixed. And yeah, we've also gotten quite a bit of positive feedback, for example, by the developer of the Jackson parser library, Cowtown Coder, Tattoo. And yeah, as you can see in the middle, this is up and running on OSS Fuzz and can also distinguish between ordinary bugs and security issues. So yeah, we would like to ask all of you to, if you maintain a library or just know of a library, to bring this onto OSS Fuzz, to let it be fuzzed with Jesser. Thank you.
Okay, thank you both so much for your talk. And I apologize, I only just realized I didn't introduce you properly. I just gave your names, not your bio. So sorry for that. I don't know where my head was then. Okay, we've been getting some questions in. But first, let me say that I think OSS Fuzz is one of the most exciting security projects out there. I think the reach of OSS Fuzz is fantastic and is a really important step forward for the community. Okay, so Net Zero is asking, how do you handle communication? How do you incentivize projects to remediate things? So not only how do you motivate them to join in the first place, but how do you keep things running once the bugs start being found?
So most of it, I would say, is all automatic. Like there is no manual communication at all. They only sign up in like this project.yaml file where they declare like the set of people that want to get CC'd on these new bug reports. And as new bugs are found by OSS Fuzz, it automatically CCs them and automatically tells them when bugs are verified. So there is no manual interaction involved at all, other than just merging in the first PR from them, which is kind of an integration PR. We encourage them to keep their fuzzers inside their repo so they don't have to ask us for reviews. So most of the glue code is in their repository itself.
Okay, and a follow-up question also from Net Zero is, how do you actually do the scheduling for all the projects? So is it kind of after major commits or after a certain number of commits? How do you decide when to schedule which project?
So given that we have limited resources, we create the builds once a day. We recently started supporting like doing 4 builds a day as well for critical projects, but eventually we will try to see if we can scale it even more, like do every commit. That might be feasible at some point, but given that we want to scale to thousands of projects, that might be hard. But still, we catch regressions within a few hours, so that's still pretty quick, I would say.
Okay. I have a question for Fabian. Regarding Jazzer, could you please share your thoughts on the difference between it and JQF, a property-based fuzzer for Java?
Right. So JQF was certainly a motivation in building Jesser, and you can sort of find some of the ideas that it pioneered, like this structured or semantic or property-based testing fuzzing in the fuzz data provider. So you have something very similar in JQF where you get a lot of Java primitive types right off your fuzzer input without much work, strings, arrays, Boolean, random choices. All this is available in Jesser. I'd say that Jesser has sort of a more modern backend. It builds on the proven lib fuzzer. It has a very good coverage instrumentation, which is Jacoco plus a few extra smarts that work very well in fuzzing. It has hooking. It has a feedback loop to the fuzzer that informs the fuzzer about string compares, magic values, all these things. So I think, yeah, it's more efficient, it's faster, but yeah, it owes to its predecessors.
Okay. And another question along that line is, how was your experience integrating Jazza into a project as large and well, as large as OSS Fuzz?
Oh, this was, I mean, apart from a very few edge case bugs, which all had to do with native libraries, which are always a bit of a complicated story in the Java world, all of this went very smoothly. So as Abhishek has said, if it works locally, it works in the cloud, and that mostly held it true. Because, I mean, the good thing about OSS Fuzz is that it doesn't have any assumptions on what fuzzers do or what they look like. You have Docker files and you have sort of very generic ways of interacting with the fuzzers that generalize to Jazza rightly. And yeah, I think we actually benefited from basically being libfuzzer plus Java smarts, which meant that we are fully compatible with libfuzzer CLI commands, and that meant that the whole process was pretty smooth.
Awesome. So Abhishek, after having integrated Jazza, what other kind of fuzzers would you like to see the community create and integrate into OSS Fuzz?
I would definitely say we are really looking for more fuzzing research. So we would want first more fuzzing engines to be tested inside FuzzBench. So things like more symbolic execution engines like SimCC would be very ideal to have it in FuzzBench, and then getting into OSS Fuzz. And we encourage the community to develop more engines. Like, we don't want to just stick to, let's say, AFL++, libfuzzer, and HongFuzz. We definitely want more fuzzing engines there.
So is there any language in particular you'd like to see more work on?
I would say definitely more work on the memory safe stuff. So like very excited about the Java fuzzing work that Code Intelligence folks did. Because sometimes we always have that convention around like, hey, we cannot find interesting bugs in memory safe language. And that's not true. Like, to give you an example, OSS Fuzz found a bug in Golang which could actually crash down most of the Ethereum network. So that's pretty serious. So we want to change that notion where people just think, hey, it's not worth it to fuzz memory safe languages. So we definitely encourage more research there.
Okay, awesome. Okay, then I have one self-declared newbie question for you both. Can we do API fuzzing using OSS Fuzz?
I think so, yeah. At some point, we would be looking into it. It's more, do you mean web APIs or what do you mean? Like,
I'm not quite sure what Taj meant. If you're listening, Taj, and can type quickly, I see keyboards are being
at this conference.
because we call it like API fuzzing. It's like unit test running the program API, but I think maybe he means web apps.
So, yes, I'm guessing. I'll also guess that it's web application APIs.
Well, I think
we're not
we
hearing
have
back
there that Microsoft research folks pointed out, so that's great. And I think, Fabian, you guys have a web API fuzzing solution too, right? So that would be very nice to integrate in OSS Fuzz at some point.
So yeah, that will come up next.
Okay, then looking at time, thank you both for the interesting talk.
Thank you very much.
Okay, then next up is our final talk before the panel. And this is about coverage guiding fuzzing of web applications, which actually probably leads on from the question we had just now. And Khaled, CTO of Code Intelligence, will be telling us about it. So Khaled is an expert when it comes to solving difficult and challenging technical problems. And as CTO of Code Intelligence, he drives the customer-oriented development of CI fuzz testing platform. As a malware analyst, he's an expert in binary code analysis and has been working in reverse engineering and penetration testing for over 7 years. And yeah, now he's going to tell us a bit about how coverage-guided fuzzing can help test web applications. Khaled, the mic is yours.
Yeah, thank you, Matthew, for the introduction. Can you hear me well?
Yeah, I can hear you and see your slides. Everything's looking good.
Awesome. So Yeah, hello everyone, and welcome to my talk about coverage guided fuzzing, or applying coverage guided fuzzing for web application. And so at FuzzCon so far, we've seen really 3 great talks. So on the one hand, Simon mentioned why fuzzing web application is currently difficult. We've also seen Restla, and Fabian and Abhishek demonstrated that Jazzer is a very effective coverage-guided fuzzer for Java. And in this talk, I would like to shed some light on the special challenges that are related to applying code coverage or coverage-guided fuzzing for web applications, and share a few insights on how we can address them. And here the focus will be on Java. And the end goal that we'd like to achieve is to make coverage-guided fuzzing usable for web apps, and as a result, enabling web developers also to benefit from this technology. So before getting started, let's discuss why web application security is crucial and why should we care about it. So as we heard, APIs are everywhere. So most critical code is in the web services, and more companies are moving towards a software as a service model to provide their services to the customers. So while this has advantages regarding deployment and updates, security flows in these scenarios have huge impact. So if you hack a client, or if you hack a single client, you only affect this client. But if you hack the web backend, basically you affected all clients, and this is really critical. And we also see that critical vulnerabilities such as SQL injection, cross-site scripting, and remote code executions are constantly found in these applications. And since the complexity of web applications is rapidly increasing, so is also increasing the need for an effective and automated test methods. So to give just some practical insights into the challenges of web applications, let's have a look at this small code snippet from web code. So web code is an intentionally insecure web application written in Java, and it's maintained by OWASP, and it's designed to teach some security lessons. And so here we see the implementation of an endpoint that has an SQL injection vulnerability, and it's there because the SQL query is executed without any sanitizations. So here we see that it's a REST controller. We see the exact endpoint, and from the method signature, we see the parameters that are needed in the post requests. So this means that the request that we should send to this application should have a very specific structure. Otherwise, the login code will not be triggered. And obviously, a fuzzer or a dynamic analysis tool that just trying some random inputs will probably never reach this endpoint. Next, we see the call to the execute query method, where the SQL query is actually executed. And so even if we manage to achieve this, to reach this endpoint, how can we tell that executing this query may result in an SQL injection? So one approach that is widely used by DOS solutions is that we have, as Simon said, we have some sort of built-in attack scenarios that attacks the application, tries to reason about the responses. However, since these tools don't look inside the application, this can be complicated by the fact that such calls might be, for example, protected in a try-catch block, and which means that this might prevent the analysis tool from seeing what's actually happening in the code, leading to either false positive or missing some code. And also, we have, program code is full of checks like this. meaning that interesting program behavior is only triggered when special constraints about the inputs are, or the requests are there. And so, for example, in this code snippet, the username of the request has to be Larry so that we can be able to execute the SQL statement. So just to summarize this, so in order for a fuzzer or a dynamic analysis tool to be able to trigger the SQL injection vulnerability, it needs to know exactly how the request should be structured. It needs to generate a request with a username Larry, and it needs to know that it has triggered an SQL injection vulnerability. Furthermore, web applications have like a more complex deployment. So here's an example of web code where it's a Docker compose file that starts multiple services. Of course, for real applications, this can get really more complicated. Applications consist of multiple microservices that are deployed, for example, in a cluster, which makes quite different from the traditional approach of fuzzing, where the fuzzer and the application under test run basically in the same process. And of course, here we don't want to only talk about problems, but in the remainder of the talk, I will try to share some insights on how can we address these challenges so that we can benefit from the potential of coverage-guided fuzzing for testing web applications. So the first challenge is that we need structured inputs. And the good news about web applications is that there are only few standard protocols that we need to support. So as we saw in Marina's talks, for REST API, we can have use the corresponding Swagger or OpenAPI definition to know exactly how to talk with the application. And so what we need is that we need the fuzzing solution to be aware of the structure. And this is known in the community, in the fuzzy community, as structure-aware fuzzing. And this means that the fuzzer needs to understand the corresponding specification so that it generates meaningful requests and perform smart, high-level mutations that would still result in valid requests. And combining this with coverage feedback is very effective. And so let's see how this can be implemented, or how we can implement it in using Jezzer. So this shows the usual workflow of Jezzer. So Jezzer would just send requests to the applications, would execute the application, it gets feedback, and based on this feedback, it generates further inputs that maximize the code coverage. And for Jezzer, we have an interface that allow you to develop structure-aware fuzzing on top of it, meaning that you can enforce Jezzer or tell Jezzer how it should mutate or change the input so that they adhere to your grammar or specifications. So for example, for REST APIs, we can, as Marina said, we can use the Swagger definition, the corresponding Swagger definition, and build on top of Jezzer the structure-aware fuzzer, meaning that a grammar, a mutator that would understand the grammar and would perform mutations that would respect this grammar. And this has the advantages that all the requests that the fuzzer would send will be valid and will be accepted by the application. And the nice side effect here is that we don't have to write fuzz tests. So have you seen in Fabian's or an Abhishek presentation, traditionally we need to write fuzz tests that would basically execute the method that you write to test. In this case, we can write or generate fuzzers without even having to write these fuzz tests. And even if for some frameworks like Spring Boot, for example, the API resolution can be done automatically. And this is, of course, you can use this interface to implement your own grammar and based on your scenario. And for that, I would encourage everybody to have a look at this in Jazzer. So let's move to the second challenge. So while maximizing code coverage and reaching deep code blocks is essential for fuzzing, the second ingredient to have an effective testing is to be able to check whether security violations actually happened as a result of executing a given request. And so traditional black box testing, as mentioned, they have some sort of built-in attack scenarios, and they analyze the responses that the application sends in order to see if any bugs have been triggered. And for example, Zap has a really great active scanners that detects a wide range of bugs. And to solve this, we have two solutions. So following the success of Google sanitizers, which basically use instrumentation to insert runtime checks into C and C++ to check for a wide range of vulnerability. And a similar approach for Java to handle these cases would be very effective. Meaning, because here we can see inside the application, so we can see how the code is executed, and based on that reason if a bug or a security violation happens. On the other hand, we can also integrate fuzzing with other Dust tools so that they can collaboratively work with each other. And let's see how the second approach would look like. So here, just a high-level overview how Dust solutions would work. Just the Dust tool, for example, Zap, would attack the application and checks if a security violation happened. And since that black box approaches, as Simon said, don't see into the code, it's hard they cannot tell if the different attack scenarios actually result in interesting or triggering new code areas or not. And so because they miss these insights. And this exactly where coverage-guided fuzzing shines. So one interesting approach would be to combine these two approaches in a way where we can utilize their distinguished strengths. So the core idea here is to use the coverage-guided fuzzer to explore the program and guide the other Dust tools. This means, for example, here, when Jazzer finds an interesting input that results in new code coverage, this input is then forwarded to the Dust tool, for example, Zap, and then the Dust tool uses this input as a seed or as an example that it can attack. And this means that we will focus the Dust tool resources only on attacking requests that have unique or interesting code coverage that we know that they reach new code areas. And this would help these tools in the Dust tools, the black box tools, in solving these the difficult checks that they struggle with because of missing feedback. And in the same way, we can use Jazzer, we can use coverage-guided fuzzing to test if the inputs that are generated by the Dust tool actually result in some new code coverage. So with this, we just close the loop and we use the fuzzer and the information that the coverage-guided fuzzer has about the application to guide other Dust tool. And this is proved to be very effective in practice. And the second solution is, and the really interesting approach would be to add runtime checks as part of the instrumentation. And these checks would just examine the state of the application or the program and decide whether a security violation was actually triggered. And to support this, Jazzer has an interface that allows you to define your own custom hooks. And this means that you can sort of register checks to be executed or to be performed at specific events during executions. For example, you can schedule checks to be performed before or after a certain method is called, or even replace a certain method call. And as an example, to show how we can detect that a potential SQL injection here happens is by using this hooking framework. Simply, we can add a check that would intercept those method calls that execute SQL queries. The check would simply execute the original method, or would call the original method in a try-catch block, and would check if an SQL exception is thrown as a result. So this would mean that the fuzzer was able to generate input that landed in an SQL query, causing a corresponding exception, which is a strong hint that an SQL exception happen or might happen. And so note that, and this method would even work if the original method call, like the execute query, happened in a try-catch or was protected in a try-catch block, because we intercepted this at the level of the function call. So since we have these deep insights into the code, we will see exactly what happens there, and we can perform really valuable checks. And so this, the hooking framework is part of Jazzer, and you can use it to implement your own checks. And the third challenge is that we have these various checks in the code, and we need to handle them automatically. And of course, it's infeasible for a black analysis, when using black analysis tool, to just come up with all use cases that are needed in this application under test. And it turned out that with coverage-guided fuzzing, we already solved this problem, because as part of the feedback that the fuzzer would get, in the case of Jazzer, is all equals operations, all string compares or integer compares, and this would give the fuzzer valuable feedback that it can use to generate smart inputs. So, for example, one thing that Jazzer would see is that here in this example, the username was compared to Larry. So one of the things that they try is just use Larry as a username and see what happens. So this is very effective. And this is, and it's also crucial to keep track of all interesting inputs that the fuzzer, so that the fuzzer does not start from the crash, from scratch all the time. And this is, of course, by design in coverage-guided fuzzing, where so all interesting inputs that the fuzzer gathered in previous runs that have a new code coverage would be stored in what we call a seed corpus. And this would make coverage-guided fuzzing a perfect fit for CI integration, for continuous integration, meaning that for each run, the fuzzer would already start from the knowledge that it has gathered through all the fuzzing runs. And so before discussing the fourth challenge, let's hold on for a moment and have a look at how would the results of coverage-guided fuzzing in web code in this example would look like when we address the challenges we've seen so far. So what the net results would be like, we have an effective testing and detailed bug reporting. And so here in this example, we see that we get the exact concrete input that the fuzzer used to trigger the SQL injection vulnerability. And we know the exact line of code that where this vulnerability was triggered. So the fuzzer was able to generate the request as expected by the endpoint. The feedback enabled it to use Larry as a username, And the runtime checks enables fuzzer to verify that it actually triggered the vulnerability. And a very nice property of fuzzing, as we see here, is that it generates the concrete input for each bug it reports. And this means that you can start a debugging session by executing the application with the crashing input and use the stack trace provided by the fuzzer in the bug report to set up breakpoints. That makes it easier to navigate through the code. And these concrete examples help developers to better understand the reported bug and be able to fix it more easily as a result. So let's move to the fourth challenge here, which is for web applications, we usually have really complex setup and deployment. The application might consist of several microservices that communicate with each other over the network. And so this makes the traditional approach of fuzzing, where the fuzzer and the system under test have to run in the same process, hard to apply in this scenario. And of course, to enable developers to apply coverage-guided fuzzing in these complex scenarios without having to make substantial changes to the way they deploy their applications, we need a better approach. And let's see how this issue can be addressed. So here we see an example project consisting of several microservices that communicate with each other. And the Java virtual machine has a very powerful facility called the Java agent. And with Java agents, we can intercept applications at runtime, the applications that are running on the JVM at runtime, and modify their bytecode. And this is the method that we use in Jazzer to perform instrumentation by inserting these coverage markers into the JVM bytecode and also all the hooks that we defined. So if we go back to our example, we can simply attach a Java agent to the microservices that we would like to instrument and test. And the agent would then perform the instrumentation. And the instrumentation would then have to communicate the feedback back to the fuzzer. And this way, over the network. And this way, this has the biggest advantage, of course, that you don't have to change the way you deploy your application in a testing environment. All that you need to make sure is that the fuzzer is reachable from the microservices, so the instrumentation can report the feedback. Here's some final thoughts. Of course, fuzzing is nice, but fuzzing is most effective when performed continuously as part of the development process. So this enables to find bugs and vulnerabilities early, and as a result, be able to fix them quickly. So, and ideally, as Abhishek mentioned, code should be fuzzed on each code change, or as a part, for example, for pull requests, as we see here. And this would enable developers to get instant feedback whether their changes has introduced any bugs. And early feedback enables developers, of course, to quickly fix the bug, since the issues and all the details regarding the change are still fresh in their mind. And a recent empirical study by Marcel Blume of all bugs in VS Code revealed that, or shown that, 4 in every 5 reported bugs have been introduced by recent code changes. So more specifically, like 77% of the reported bugs were only regressions. And this shows that continuous fuzzing is essential when it's done continuously, and it needs to be integrated into continuous integration to make sure or to guarantee the security of the software. And as discussed, coverage-guided fuzzing fits perfectly, since it keeps track of all interesting inputs that are generated over the time. And this continuous fuzzing would also enable you to get an overview about the evolution of the security of your application over time. So to conclude my talk, I hope I was able to show that instrumented fuzzing improves web testing immensely. It has it can achieve high code coverage with improved bug detections if we use them based on the instrumentation, and it has a perfect fit for CI/CD integration. So with that, it's a very effective method and to guarantee the security of web application. And so with that, I come to the end of my talk. And so thank you for listening, and I would be happy to take any questions.
Yeah, thank you, Khaled. That talk very nicely tied together all the other talks previously. And we've got a couple of questions. And the first one is from Taj, who says, fantastic session. Can we have some documentation to get started with Jazzer on web-code applications?
So we will add a blog post in the Zap blog post, Zap blog. So we'll have some insights about how what we do in order to test web application with Jazzer. So stay tuned for that.
Yeah, so follow Khaled on Twitter, Khaled Yakdan, and you'll definitely hear about where the documentation is going to be released. Then Mehdi asks, how does Jazzer compare to Restler?
So Jazzer, the main difference is that Jazzer is coverage guided, while Restler is black box. But as I show in the example where we can integrate Jazzer with other dynamic analysis tools such as Restler, so that Restler can benefit from the instrumentation capabilities of Jazzer.
And there's actually a follow-up question by Mehdi. He says, not sure if I understood correctly, but it looks like you'd have to instrument the backend code to be able to fuzz with Jazzer.
So of course, you have to instrument the code so that the fuzzer will get the coverage feedback, so that it knows I sent this request, and with that, I was able to reach these code areas. So for coverage guided fuzzing, you have to instrument the code, yes.
If I understood that correctly, that's what's done by the Java agent, right?
Yeah, exactly. So in the context of web application, you just have to attach the agent to the service you'd like to test. This would automatically instrument it, and the instrumentation would then report the feedback back to the fuzzer.
So this happens automatically. It's not something you as a developer actually have to manually do.
So you can imagine it, you have your own deployment, as you don't have to change anything about that. The only thing that you have to do is just add or load this Java agent in the microservice. All the instrumentation and reporting would be done automatically, of course.
And I have a question which came through the private channel, and that's asking, can Jazzer look for SQL injection XSS vulnerabilities? Yeah,
so Fabian showed how we found cross-site scripting, vulnerability in the JSON sanitizer, and I showed an example of how we used instrumentation-based bug detectors to find SQL injections. Yeah, and the good thing about that is that you can, with instrumentation, can see exactly what happens in the code. So you can, even if, for example, the execute query statement is called in a try-catch block, you can still exactly see what's happening inside with the Hugging framework that Jazzer provides.
Okay, then looking at the time, we have one final question from NetZero, who's asking if he was developing an Android app with Kotlin or Java, would he be able to use Jazzer for that?
So with Jazzer, you can of course instrument the code. It's not officially supported. We need some modifications to support that, but it's not supported off the box, but it's not hard to do as well.
So keep tuned for that.
Of course.
Okay. We have one last question from Benaz. Do you have any plans to utilize the client-side analysis to enhance your tool? Because a large portion of the application logic resides on the client side in modern apps.
the question would be if it's, or how interesting is to test the client side, because usually when you test the backend, there you have the huge impact. Because if you attack a client, basically you just affect this one. But if you fuzz the backend, there you will have the most interesting vulnerabilities. But it wouldn't make a difference if it's a Java application where you have an API. You can either use Jazzer to test specific methods, or use the sort of the enhanced form to test your application, of course.
Okay, well then, thank you very much, Khaled, and thank you again to all the speakers who kept time perfectly today, and we had no technical glitches up to now, so I'm very happy about this. So now we come to the last part. We have the panel discussion where all the presenters will come again, and they'll be joined by Sergey Dechant, the CEO of Co-Intelligence. And the panel will be led by Boris Paskalev, who's the head of product for AI code analysis at SNCC. Boris has an executive MBA from Triumph, as well as MSCs and BSCs from MIT. And since we have a tech audience, I'd just like to elaborate that Triumph is in the lines of the NYU Stern School of Business, the London School of Economics, and the Heck School of Management in Paris. So a very illustrious combination there. Boris has worked at various financial and tech companies, Putnam Investments, Opnet, and Deutsche Bank, before establishing a successful 15-year career at Vistaprint, the largest online supplier of physical and digital marketing products for small and micro businesses. In 2017, Boris co-founded DeepCode AI, the first AI for software code that can learn from billions of lines of code and extract knowledge of the global development community. Enabling AI-biased detection of security and reliability code issues named Grammarly for coders. DeepCode is an excellent example of modern AI systems that can learn from data, software code in this case, yet remain transparent and interpretable for humans, aka symbolic AI. Together with his friend and co-founders, an amazing team, Boris led DeepCode from an ETH spin-off to being acquired by SNCC, where he's currently the head of product for the AI code analysis. So let's welcome Boris as the head of the panel, and you can take it from there. Welcome, Boris.
Welcome, everyone, and apologies, Matthew. I didn't know you're going to read all of this, otherwise I'm going with this.
Well, it's all interesting, so I'm glad our audience knows this.
Super. No, it's great. Great presenters, great talk. So let's come together and ask them some cool questions.
Okay.
Sergey, hello.
Hi, Boris.
So for everybody, feel free to type in questions in the Slack channel for panel or general. We'll see that as well. I have prepared a couple just so we get everybody there, and the speakers feel free to join in as you can. I think you can turn on your cameras, but just mute yourself every once in a while. I think that's the setup. So I'll start with one question just for everybody to see what they think. And we saw a little bit of an impact what each tool actually does today. And I was wondering how you envision those tools to impact the development community in 5 years. You can answer it in kind of number of developers that are going to be using the tools, or number of projects that are going to be covered by it. I'm just curious what your visions are.
Sorry, I didn't get the question. I had a few connection issues. And also, is Simon and Marina missing, or I just don't see them? So, oh, there he is.
Simon's coming. Good.
Yeah, I think there's people up on screen at one time, and I don't seem to be able to turn my camera on, but I can turn audio on and off.
Okay, so they are in the talk here. Okay, perfect. Boris, could you please repeat the question, because I was handling those kind of issues here. But sorry.
So the question is for each tool, where do you see the tool impacting the development community in 5 years? You can say, hey, today we're covering X developers, X projects, but in 5 years, we believe we're going to be here and we're actively working towards.
Okay, so if we are saying it would be over 1,000 developers right now, but in 5 years, obviously, I see that we will move away from all those marketing terms, DAST, SAST, and so on, because I think that most of the tools or the players there will kind of make an all-in-one solution, because basically static analysis is something where you get immediate feedback in your IDE, and if you are part of the continuous integration, it definitely needs to be something dynamic. So whether it's coverage-based fuzzing or black box fuzzing shouldn't matter, but in the end it will be a combination on that. And I mean, since you are at SNCC, there is also the software component analysis, and this is another thing. So basically, I think that most of the players will kind of have an all-in-one solution, and obviously we want to get there as well. And fuzz testing is one of the techniques making it possible, because so far dynamic analysis was too hard to use in continuous integration. But with all those kind of advancements, it will be definitely possible.
Very cool. So you're seeing an integration of all the systems together for one covers it all. And I think I want to hear Abhishek, because OSS Fuzz is pretty much trying to do that. Kind of allows many tools to be together as well. And Simon, if you think that Zap's going to be there as well.
Yes, definitely. So I think in 5 years, we would be hoping that we don't have to really spread the word on fuzzing, like it becomes as standard and ubiquitous as testing itself. So we would more likely see like frameworks where all of these fuzzing tools, fuzzing engines, like tools like Zap, or like fuzzing engines like LibFuzzer and AFL++, those are all integrated in this framework, and then people just write these unit tests next to, or like fuzzer tests next to their unit tests, and it becomes completely ubiquitous and transparent in that way.
Got it.
Thank
you. Simon, before coming to you, ladies first, Marina, just a quick question. Is Microsoft planning to actually join that and actually adding Wrestler to the OSS Fuzz?
So I don't know if I can comment on like those type of product future plans, but I will say like where I hope Wrestler gets ubiquitous use like over the next 5 years is in kind of the services deployment pipeline. So right now, this is seems from our experience, it's a very much non-standardized kind of space. So we hope that over time there's going to be like more widely used standard frameworks that fuzzing can plug in at the right time and with the right environment, and kind of package all of that together.
Very cool. Thank you. And Simon?
So I mean, how many people will use Zap in 5 years' time? Well, I don't even know how many people are using Zap right now. We're an open source tool. Anyone can download Zap. Anyone can run Zap. We get a couple of things. We get a ping when Zap starts. We get a check for update ping, but those can be disabled. And so it's very difficult to even know how many people are using Zap. We get download counts. So I know, for example, that last month we had 6 million Docker pulls. So I don't think Zap was run 6 million times, but we're talking big numbers here. And I think you have to realize there's a difference between commercial tools and open source tools. And so commercial tools are not going to have the same reach as open source tools for a long time, if ever. And I think you also have to realize that if with fuzzing tools you have to write fuzzing test cases, that immediately cuts down the number of people who use it. If people have to do anything apart from flip a switch, then that immediately massively reduces how many people will actually use that tool. I wish it was otherwise. But so I think there's going to be, I agree with what was said before about there will be, the tools need to come together. We need to, at the moment, we've got lots of different security tools working in different ways, and there are good reasons for that. And they don't, we can't say one tool is better than another tool apart from particular circumstances, and all tools have their strengths and weaknesses. So I think we need more integration between those tools. we've already seen how the feedback-based fuzzing can really improve DAST, and having a knowledge of the source code really helps. So the tools need to come together and work together. Whether we have, there will be some commercial tools that will do everything. I don't think they're going to be cheap. So for the mass use, particularly in open source, unless the individual's tools come together and work together, we won't get that kind of adoption that we need.
Interesting. But yeah, good point. I think most of the other tools already said that they have pre-configured tools. So, and one of the measurements we're hearing is kind of how much things you cover out of the box, which is very nice. I actually do hope that actually commercial tools, there's a good trend that they're actually free for open source anyway. So even if they are so great, expensive yet for commercial use, they will remain free for open source. So I think that's a good trend there. Anybody else wants to add anything on that topic? Otherwise, I'll jump for something else. Let's see if we have more questions in the chat. Nothing yet. Then I'll throw another one that actually Touch asked in the general channel, how can we get started with the web service fuzzing? And I want to understand clearly. We actually got an answer that with if you have a definition of the service and or your APIs are actually open API, you can start that quickly with Zap or Wrestler. But the question is what is the setup time required? I mean, including like if you have out-of-the-box settings that you can count that in, but in hours. How much time does it take to set up fuzzing for web application, like small size website, e-commerce, whatever that is?
Well, this of course depends on the application and the complexity of the application, but it can be done in a few minutes. And if you're talking about simple applications, like if the example we showed with web code, you just need the API and the API definition, and the fuzzer will just automatically understand that, and then based on that, just perform its mutation, so you can get up and running in a few minutes. And this is just based on what Simon said. This use case where you just have the API definition and you automatically generate the fuzz test. This would reduce the barriers for developers to use it, because they don't have to write fuzz tests. And so that you can get up and running in 2 minutes, actually.
Got it. And I'm assuming that that's similar for the Zap and the Wrestler tools, that they're pretty easy to set up and people can start using them immediately. Is that the case?
With Zap, definitely. I mean, we've got Docker images you can pull. We've got a desktop application. And I mean, the desktop is quite good because you can then see what's going on inside Zap. You see the site map, so you can actually, even if you want to end up automating, I always recommend you start with the desktop app, so you can actually see what's going on, see Zap's understanding, and then configure it to improve it. But we have things like GitHub Actions. So you can just include GitHub Actions right now. So Zap isn't even running on your own infrastructure. So yeah, very quick to set up, but to get the most out, you still need to take time to understand how Zap understands your application and potentially tune it.
Got it. I think, Abhishek, you already answered in your presentation that it's pretty automated and everything is very nice workflow, so developers get even reminders and everything, which is pretty cool. And Marina, from your perspective, how long does it take to set up an initial run?
Yeah, so for Wrestler, it's minutes to set up an initial run. I think the biggest next step that still can take a little bit of time, just depending on what resources you already have, is setting up the authentication. So it's very flexible, but if you have very standard token-based auth, you need to have some kind of a program that does the authentication that you pass to the tool. So, it may take you 10 minutes. If you already have that, it may take you an hour. If you need to write that, if you know very little about authentication and you kind of have a service you need to attack, it may take you a day. It just kind of depends. But after that, like Simon said, it depends on how much coverage you want to get out and how complex the app is. So in some cases, we've had the authentication we can reuse, and it's 100% coverage out of the box. And those are yes, this is awesome. But it's not always like that.
So in short, everybody can start using all those tools pretty quickly. So definitely try them out. I'll recommend. Authentication problems, I think Simon highlighted, you can do it in test mode, bypass authentication. I think that's It's a brilliant hack, in my opinion, not have to deal with authentication, clearly not always applicable. But that's very, very nice. So everybody, you can jump onto it very, very quickly, which is nice. Okay, so let's see questions. No questions so far. Up now I see. Well, this is cool. Get GitHub Actions. Yes, actually, GitHub Actions was very cool. And I was surprised that you actually have architectures for Zap that like the OSS fuzzes. Actually, you don't have to run it on your own, which is nice. Web services for everything, which is great. Okay, so just a very quick question. What tools do you actually use in your internal environment? And that's kind of a question for everybody, again, for code quality and security today. I'm just very curious. Dog fooding obviously being one of them, but what else? Nobody wants to answer that question.
I'll jump on for that.
So
we use static source code analysis for Zap. So it looks good to me. It's actually worked very well for us. We actually also have a bug bounty. So if you can find a remote code execution on Zap, and that includes via our heads-up display, then you'll get $1,000. So I think there's static source code analysis. We don't really, I mean, we have the HUD, that's kind of different interface. So we didn't have a web interface for us to test, but static source code analysis is good.
Very cool. Abhishek?
Yeah, so we encourage our security teams and developers to use the same tooling that we use internally, or the same tooling we use internally as well. So if you think of ClusterFuzz, which is fully open source, that's the same infrastructure that's used inside Google as well in all of the different product areas for fuzzing. So yeah, we do the same fuzzing engines, which are all open source, like LibFuzzer, AFL, HonkFuzz. So that's our vision, which is security shouldn't be kept confidential, or it should be always open source, shared with the community, and we should all build up on it together.
Very good. Sergey, do you want to share for Code Intelligence?
Yeah, so a fun fact, we actually used fuzzing to find bugs inside the fuzzer. So we found a few of them. So this was really nice. Yeah, and for the C and C++ parts, we use a lot of CLang checkers, because those are as well pretty good. Yeah, maybe Khaled could share a few other things.
Yeah, so basically, yeah, regarding security testing, of course, fuzzing is a great tool there. We also perform all kind of unit testing and system tests, and because with fuzzing we can find edge cases, but you'd also like to find to make sure that we functionally everything is fine. So also, of course, static analysis for some parts. So
got it. Thank you very much, Khaled. And Marina?
Yeah, so I wasn't sure actually what the question is about, but so I'll answer it in the context of Wrestler and kind of the Wrestler-related tooling. What do we use? So I think for security, one of the biggest things we take advantage of is Microsoft's kind of static code scanning and security checks out of Azure DevOps that currently exists. And this has some components that are publicly available, some kind of more private components geared toward Microsoft. But this is great because just by checking in code, you automatically get those running, and they actually find issues on a regular basis. And so that CI/CD workflow is just huge for us. And then I think for code quality, interestingly, the biggest bug finder and kind of ongoing quality monitoring for Wrestler would be the real world API specifications that we find, and kind of the real services across the company that we just were like, oh, well, we are hardening Wrestler for open source. how are we going to do this? Well, we're going to point it at all these, very complex API specifications that people have written. We don't really have handcraft our own, both for time reasons and because, we really want these to work on, all of these public APIs out there. So that's been kind of the biggest impact for us.
Got it. Thank you very much. I appreciate some of it could be confidential, so appreciate it. And then I'll go with another question, which is recommendation to the whole audience. So now that we heard about all those tools, what would be your recommendation for next steps? We knew what the vision is going to be in 5 years. All the tools are going to be connected. But if I'm not using fuzzing today, and I'm sure some of the people in the audience might not, like, which tool should I start using? Do we just jump together and put them all in, or do you pick and choose?
Well, I think it's worth talking about security tools in general now, because I think if somebody isn't, if people aren't using any security tools, then it's quite overwhelming. And there is advantages and disadvantages of all of them. Personally, I'm going to say DAST is a great start, and because DAST is the applications, the attacker's view on your system. Things like SAST, if you're using closed source, your attackers hopefully don't have access to that, so they can't find the bugs immediately. But with DAST tools are acting as the malicious attackers. So they are doing what the malicious attackers can do, and therefore, if you don't do any, I would start with DAST. But DAST is not a silver bullet. None of the tools are silver bullets. And I think the key thing is, find out what works for you and then use that as much as possible.
Yeah, totally agree with Simon. And also one advantage of using dynamic analysis is that with dynamic analysis, you would get a proof, like for this bug, this is the input that would trigger it, so that it would give you a sort of an actionable item that you can, as a developer, have a look at what's happening there. Compared to static analysis, where you have this could be something there, but I'm not sure, might be false positive. So this would be harder for developers to just accept it. Maybe after some time they would just say, okay, it's false positive, just don't bother looking at the bugs there. But for DAST, it would be, I would start with that as well.
Very good. Yes. And Abhishek, your opinion?
Yeah, I would definitely recommend using like fuzzing as a way to find security vulnerabilities and stability issues. We have quite a bit of nice fuzzers written for all the different languages. So at this point, if you are looking for, or if you have your source out in the open, like I would definitely recommend OSS Fuzz. Otherwise, if you are doing on-premise thing, we definitely have like cluster fuzz infrastructure, which you can run at scale, and it already supports all these tools natively. But I would just say, like, yeah, start somewhere. If you have questions, feel free to reach out. The community has developed like some really great things in the fuzzing space. And I would say fuzzing is definitely very useful because there is almost like zero false positives there. Like it's all dynamic runtime stuff. So it can be very well automated. It's mostly automated. So that's the advantages of it. You can scale it pretty easily. So to give you an example, like OSS Fuzz, we don't have to do management of those 400 projects. It cannot scale with a team of any size. But it all works because the flows are all automated.
Oh, no, it makes sense.
And one big thing, yeah.
Sorry, go ahead.
One big thing I want to really stress out, which I think a lot of the other speakers have mentioned too, it should be continuous testing. Like no matter what you do, you have to make sure it's in your continuous development workflows. It shouldn't be a one-time thing because that doesn't work and you will have regressions every time.
So I will say one caveat to what I said before, and that is if it's a completely new project where you're starting a new code base, then get static code analysis in there right at the beginning. If you're applying static SAS to an existing code base, it can be a nightmare because you get a huge number of findings and just triaging them is hard. But if you're starting from a clean slate, static code analysis, keep everything as clean as possible, and it'll make things so much easier for you.
Yeah, fair point. But yeah, dynamic is, those are all 0 days, right? Because if you can find them, the attackers can find them. So it's a good point. Mariana, you're on, so go ahead.
So I agree with everything said so far about fuzzing. I just want to add one point. If you've done like no fuzzing and very little kind of a security assessment, I would start with doing like some kind of attack surface analysis, and then just try to fuzz like the one, very critical target, if you can find it. And that just really helps you feel good about getting results. Like you may have like lots of unexplored things out there, but you're able to prioritize and really get a sense on, delivering some value quickly. So like with Wrestler, we give you ways to do like a regular expression where you can really just fuzz the one endpoint that's like the really important one, and you don't have to, wait for results or have to go through a lot of things, right away.
Sounds good. Thank you very much. So there was some questions in the panel. One of it was, what is the false positive rate of the different fuzzers discussed today? I think we answered it in the previous discussion, which is almost zero, right? That's one of the benefits of dynamic analysis, because you really have a problem and you have the exact way to actually repeating it, right? Like what you have to do to repeat it. I mean, I think Marina mentioned an example where like a crash was by design, so that you can count as false positive, but also rare, obviously. And then another question came in. So if I was setting up a CI/CD myself, what do you guys recommend if I do want to use GitHub GitLab for CI/CD? And that's coming from NetZero.
So it depends whether it's an open source project or commercial, because for open source, obviously there is OSS fuzz and just go with it. If you have commercial projects, probably you are not able to use cluster fuzz for some reasons, and then obviously you have to go for some commercial solutions to do the proper integration, or you build something yourself, but it just takes a lot of time because you have to consider how long do you run the fuzz test, when do you stop, and stuff like that. And usually if you are running something like OSS fuzz, or in our case, code intelligence, someone is taking care of that. So it's obviously a matter of what kind of project you have.
Yeah. And Simon already said that they have GitHub Actions directly, so definitely add them on, especially you don't need architecture, they run it on for you, so sounds good. And for OSS Fuzz as well, I heard that's the case, so it's very easy to integrate and start using it. Marina, from your side?
Yeah, just a quick note. So I didn't get a chance due to time constraints to present in detail the REST API fuzz testing toolkit that also is developed by Microsoft Research. This gives you a Docker-based environment that you can either deploy to Azure or you can put into your own system in its local mode. And that gives you certainly optimized for Wrestler, I would say, REST CI/CD environment that we already have out there for you. It's open source, so you can try it.
Okay, super. So sounds like all tools are possible to be easily start running. And Abhishek, do you want to highlight anything for the OSS fuzzer?
Yes, so one advantage you get with OSS Fuzz as well, which is it will execute your fuzzers at scale, but you get the CI/CD integration as well. So we have a solution where if you have signed up for OSS Fuzz service, you can also have the same fuzzers run at scale in your CI pipeline. So that comes for almost free. You just land a file and it runs with every commit you have.
Sounds good. Super, yeah. And Simon wrote how easy it is to run Zap anywhere that supports Java or Docker, of course. So with that said, I think we have less than 1 minute of time. So I'll let it open for one more question, actually, or give it back to the host to do some closing remarks, obviously. So last chance for a question, anybody? Okay, then back to our hosts.
Oh, thank you, Boris, for leading that very interesting panel discussion. Thank you to all the speakers. Yes, that wraps up our FuzzCon conference today. Thank you all so much for attending and for all the great questions you asked. I hope you took a lot away. I know I did. So yeah, thank you to all the speakers, thank you to all the audience, and thank you again to Code Intelligence for organizing all of this. It's rare for an online conference to go down with so few technical hitches, so well done to the tech team here. Thank you very much, and I wish you all a good night or good afternoon, depending on which time zone you're in. Bye.